Okay. All right, so this is pretty much just going to be the review of those last few chapters. So chapter 10, chapter 12, and chapter 14. So just as a refresher, what was chapter 10 about? Like, what did we look at in there?
We covered the parabolas.
Parabolas, and we did them up, down, left, and right.
Mhm.
What else?
Ellipses.
The ellipses, so like the stretched out circles.
Mhm.
And there was another,
The hyperbola.
the hyperbola. So that was like the kind of like two parabolas, um, kind of back to back. So one up and one down, or one left and then one right. So all of those three things, along with circles, which we did all the way back in chapter 1. So those four different classes make up conic sections. So that was the bulk of the chapter. And then we went into 10.7. And what was that about?
Parametric equations.
Parametric equations. So what did parametric equations actually do?
It combines two equations with time in it.
Mm-hmm. Yeah, it takes like a regular equation, like something with x's and y's, and it splits it apart. So that way you can look at like just the x values and how they're moving, and then just the y values and how they're moving, and all of it is with respect to time. Um, Nicely done. So we looked at like how to take, like, if you had a set of parametric equations and like kind of put them back together to get just a regular equation. And then we looked at the graphing and then how to set up the orientation. Okay, so we're going to start there with those parametric equations. Because somebody asked if we could do that. So they were asking about specifically from the study guide. Number 7. Okay, can everybody see this okay?
Yes.
Yeah, okay. All right, so this is from the study guide, and it was number 7. So it was write the corresponding uh, rectangular equation by eliminating the parameter, and then sketch the curve, label any intercepts and asymptotes. If there are any, it's not guaranteed that you're going to have them. Excuse me, and then indicate the orientation. Excuse me. Okay, so 7a had a trig function in there. 7b had an exponential. Parametric equations, like you could encounter any type of equation that you've ever seen before, or any type of function. So that includes the trig functions, the exponentials, logarithms, radicals, absolute value, lines. Um, it could be anything because you guys have all experienced them and you're supposed to be able to graph any of those types of functions. So just be aware. Um, it's not just going to stick with what's on the study guide. It could be any type of function. All right, so 7a, that x is equal to 2t, and y was equal to sine of 2t. So something that people like to do is they like to ignore the first sentence. And the first sentence says, write the corresponding rectangular equation by eliminating the parameter. So what people do is they just ignore that and they don't actually give any rectangular equation, and then they automatically lose some points. So if it wants the rectangular equation, you need to state it somewhere. So this one is not going to be too bad, because you know that x is equal to 2t, so we can go ahead and use it over here. You can just replace that 2t with the x. And so there's your rectangular equation, y equals sine of x. A lot of times you will have to solve for t over here. And if you do it, if you did it with this one too, that's totally fine. You can get t equals x over 2, plug it in, and you end up with the exact same thing. All right, so sine of x, we know what it looks like, so we can graph it. But there is a restriction on the t values. T is going between negative pi less than or equal to t, which is less than or equal to pi. So we need to figure out how that's going to restrict, if it does, the x's and also the y's. So with the x's, since pi is stuck between negative pi and pi, if you multiplied it by 2, that would mean negative 2 pi is going to be the lower bound, and positive 2 pi would be the upper bound for 2t. Well, what does 2t actually equal? What's it say that 2 pi or that 2t actually equals?
X.
X. So x is going to be between negative 2 pi and 2 pi. So when you draw the graph of sine, you just want to make sure that you're only drawing from negative 2 pi to 2 pi on the x's. Now for the y's, there's an automatic restriction with this, since y equals sine of x. So the y's are going to be stuck in between negative 1 and 1, just like they always are. Like there's no fancy thing with this. So it was mainly just the x's that are having a special restriction on them. Okay, so now sine, where did we normally start it? Like, did it start at the origin? Did it start up above, down below? Where did it start?
The origin.
It started right at the origin. And then did it go up or down?
Up.
Went up. And then it was just that wave. Okay, so 0, pi, and 2 pi. So there's the right half of it. So we've got this part. Now we just need to extend it to the left all the way down to negative 2 pi. So just like that, label your intercepts. It's bouncing between 1 and negative 1. And there's your curve. Okay, now the last part of it says, and to indicate the orientation. So that by itself, the orientation is worth a point. So if you don't put it on there, you're automatically going to lose a point. So it's an easy point to get. So stick it in there. So we need to see if the curve is going, off to the right, or if it's going to go off to the left. So as t gets bigger and bigger and bigger and bigger, what's happening with x? And if you don't know, then just make a little table. If you can't do it in your head, or you're just like, I don't know how to, just take some values for t and plug them in. Like you just chose like t equals 1, 2, and 3. If t is equal to 1, what's x?
2.
If t is 2.
6.
If
Or
t is
other.
4.
6.
And if t is 3.
6.
That's the 6.
Yeah.
So as t is getting larger and larger, what's happening with x?
Getting larger.
It's getting larger and larger. So if x is getting bigger and bigger, that means everything's headed off to the right. So you want to put your arrows in there so that if you were walking along this curve, you're going to go off to the right. So stick at least 2 arrows in there. You can stick more in there if you want. I mean, you can stick arrows all over the place. Just not on the end points. Don't stick an arrow here and don't stick an arrow here, because that means you're just going to extend it, and the graph is not extended. And if you stuck an arrow on this side, that means you're in the opposite direction. So just stick at least 2 arrows somewhere like along the curve itself, not on your the ends. Okay, any questions on this? Okay, so just again, it's the question is looking for the graph, the orientation, as well as your rectangular equation. Also, kind of, if you don't put a rectangular equation for some of them, it's like, well, how did you know what the graph looked like if you didn't actually give me the equation? Kind of gets me to wonder some things. Okay. Let's go over one of the quiz questions. It wasn't on this last quiz. I think it was on the one before. I think it was either quiz 10 or quiz 11. I can't quite remember. But it was the same type of thing. You know, graph the parametric equations, give the rectangular equation, da 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 da. And there were 2 versions. One of them was x equals sine of t and y equals cosine of t. The other problem is when the trig functions were flip-flopped, but you do them pretty much in the same manner. So with these, we're going to use a trig identity. We're going to use that sine squared plus cosine squared is equal to 1. So it's just a Pythagorean identity. And now you can just directly plug in x for sine, y for the cosine, and then just square them. So that would be x squared plus y squared is equal to 1. So here's your rectangular equation. Now you get to graph it and then put in the orientation. So x squared plus y squared, what does that look like? Like, what would it graph you?
Circle.
It was a circle. And what's the radius?
It's a circle, right?
It is a circle. And then it's the radius.
Wouldn't it be the unit circle, kind of? Like the radius would be 1.
The radius is 1. Because the radius, whatever this number is over here, you square root it, and then that would give you the radius. So yeah. So yes, it is basically the unit circle. So there's the origin, you got your intercepts. 0, 1, 1, 0, 0, negative 1, and negative 1, 0. So there's your graph. And now you need to plug in the orientation. So it's kind of the same thing. Like what's happening as t gets larger and larger, what's happening with x? Is it getting larger and larger, or is it getting smaller and smaller? So you can always make a table to visually see it, or you can do it in your head too. It just depends on how proficient you are at it. So when t is equal to 0, what's x? So like what's sine of 0? Uh-oh.
0.
Yeah.
0. Okay, so when t is 0, x is 0. So we're actually starting up here at this one. So now let's let t increase. And since you're using trig values, or since we have trig functions, let's choose nice numbers for t that we actually know how to evaluate. Like don't plug in 1, because that's not really helpful. Like you don't know how to evaluate that without a calculator. So choose the angles on that unit circle. So like pi over 6. So what's sine of pi over 6?
1/2.
Yeah. We can skip to like pi over 4.
Yes, square root of 2 over 2.
Square root of 2 over 2. And if we get it all the way up to pi over 2, that's going to equal
1.
1. So as t gets larger and larger, what's happening with x?
It's also getting larger.
It's also getting larger. So if it gets larger and larger, which direction is that going? Is it going to the right or to the left?
Right.
It's going to the right. So at the start, it's going off to the right. So it's going around this way. Now, when it gets to this point over here, what's it then going to have to do?
Go to the left.
Yeah, it's gonna switch and it's gonna start to go back over here because you're on a circle. So you're not strictly just going to the right. Like right after pi over 2, like if we plugged in another value for t, like 3 pi over 4, you would get root 2 over 2 again, plugged in 5 pi over 6, and you get a half. So as you went past pi over 2, your values for x started to decrease. So they went higher, and then they went lower. So you just started to walk around the circle in a clockwise direction. Now, the other problem on the quiz, when the trig functions were flipped, so like x was cosine and y was sine, it gave you the same equation, it gave you the same graph, but the orientation was reverse. So the orientation went clockwise on that one. So if you're struggling with the orientation, I just don't know what, just plug in values for t and see what it does. Like, does it increase? Does it decrease? What's it going to do? I mean, on a circle, like once you figure out which direction it's going to go, you have to walk around the circle. You can't like jump around onto some other curve. Okay, any questions on that one?
Asher?
Yeah.
So we also can plug in the table for the y equation, right? It's gonna give us the same orientations, isn't it?
Say it again.
Yeah, I talk about the y equation. So we also can plug in the t tables for the y equations, right?
Oh, sure. Yeah, you can. Yeah, you don't have to do it with x. You can also do it with y if you want. You could do both. You just need to do however much you need to do to figure out the orientation.
Okay.
So I usually go with X because it's usually the less complicated function. Like on 7a, it was easier to use this function than it was to use this one. This one, it didn't matter. But yeah, you can totally use the Y if you want as well. Mm-hmm. Okay, any other questions?
There's another question on the quiz where it had us like the equation came out to be like y equals t squared plus 4 in parentheses or something. And I didn't know how to find the domain and range for that one.
Oh, was that? I think it was.
Because like it was x equals square root of t plus 4, and then y equaled like the absolute value of t.
It was in quiz 10. It was
Okay.
question 5, where x equals root t plus 4, and then comma, y equal the absolute value of t.
Okay. And there was no given
No,
restriction on t, right? It was just this.
Yeah.
Okay. Okay, so if we look at this equation right here for the x's, what's the smallest number you could ever plug in for t?
-4.
-4. So even though there wasn't a restriction on t that was given, there still is an implied restriction just based on the function. So we know t has to be greater than or equal to -4. All right, now on the x's themselves, x is equal to a square root. What kind of numbers always come out as square roots? Well, if you square root pretty much anything, it's always going to be what?
Positive.
And then there's one exception. What's the square root of 0?
0.
0. So we know that x is going to be greater than or equal to 0. So because of that, that means when you go to draw your graph, you can't be over here on the negative x's. Your entire graph has to be over here on the positive side. Okay, now let's look at the y. Y equals the absolute value of t. So what kind of numbers come out of absolute value?
Positive numbers.
Positives, or
0.
what's the absolute value of 0? What's the absolute value of 0?
0.
0. So y is also going to be greater than or equal to 0. So when you draw your graph, it means you've got to be above the x-axis. So with these two restrictions, where x is positive or 0 and y is positive or 0, that contains your entire graph to quadrant 1. You can be on the x and y axis, but you can't be in quadrants 2, 3, or 4. Equation, solve for t, so square both sides. We'll move over the 4. And now that you know what t is, now you can stick it into the y equation. So y equals the absolute value of x squared minus 4. So this is what we're going to have to ultimately graph and then use our restrictions and whatnot. So for starters, let's just take the absolute value bars off. We're going to kind of build our way up there. So y equals x squared minus 4. What's that the graph of?
A parabola.
Mm-hmm. Where's the vertex?
0, -4.
Yeah. So it's just your regular happy face parabola. Got shifted down by 4. Your intercepts would be -2 and 2. Okay, so that's just the x squared minus 4. So now let's slap the absolute value bars back in there. So absolute value, like what does it do to numbers?
It makes them flip. It makes them positive.
Makes them positive. So that means, like we discussed before, like you can't have any negative y values. So it doesn't erase them. It flips them because absolute value makes them positive. It doesn't make them disappear. It just makes them positive. So any negative y value, the stuff that's down here, it now gets flipped. And it does something like that. So instead of having it down here at -4, it's up a +4. Your intercepts are the same, as well as these positive sections here. So if this was all you were graphing, this green one, your graph would look just like this. But that's not where we started. We started with these parametric equations. So we know that t has to be greater than or equal to -4. So if t is equal to -4, what is x equal?
0.
0. And what would y equal?
4.
4. So that means your curve we can only keep that much of the graph, which we said earlier, we're restricted to that first quadrant. So this green curve, we can only keep whatever was in quadrant 1. And now you got to do the orientation. So as t gets larger and larger and larger and larger, what happens with x? Is it getting bigger and bigger, or is it getting smaller and smaller?
Bigger and bigger.
Bigger and bigger. So if you were going to walk the curve, you would be headed off to the right. So stick your 2 arrows in like that. All right, any questions or steps on that one that you have anything about?
I have an off-topic question if you don't mind.
Well, are there any other questions on this one?
No.
Everybody's good? Okay, all right, Michael, what's your question?
When it comes to logs or natural logs, can you give me an example of natural logs or yeah, just logs in general?
like, are you talking about chapter 5 stuff?
Yeah, just like example of like when it for how do graph a log or any type of log. Yeah, pretty much. And just have restrictions and like kind of similar to question number 7, like parameter that.
The parametric equations.
Yeah.
It's like I can relate it to a parametric equation, but otherwise, like the chapter 5 stuff, I'd rather go into like what the exam topics are going to be.
Okay.
So I don't want to do a full review on logarithms, since that's not what the the exam's over.
Okay. Yeah.
Um,
I'll move forward then.
I know 7b has like a logarithm and it's like a parametric equation.
it's like, well, 7b has an exponential.
Those
It's like
E-
this is your guys' review. So if you want to just keep doing parametric equations, we can keep doing them.
well, I don't want to waste anyone's time or anything.
Okay, so t has to be greater than or equal to 0. What kind of values could x be? Can they be positive? Can they be negative? Both? Do we have to leave out 0?
It has, well, x has to be greater than 1 or equal to, right?
Greater than or equal to?
Greater than or equal to.
Okay. Yeah. So t is, or 0 is the smallest number you can plug in for t. She's right, because e to the 0 is just 1. And then as t gets bigger, x is going to get bigger and bigger. All right, so if we take this equation and solve for t, what gets rid of an e?
ln, is it?
ln. So ln both sides. And it would look like that, and then the ln and the e cancel out. There's your t. So you can plug that in for the t in the y equation. So y equals ln of x.
And that will be 1, correct?
It would be 1.
Y equal Lx is 1.
No, y equals ln of x is a function. It doesn't, it's not a number.
Oh, okay.
ln of e would be 1. But yeah, just ln of x is just ln of x. All right, so the graph of ln of x just goes like that. It has an intercept of 1. It has a vertical asymptote at 0. But we need to remember our restriction on the x's. So x can only be greater than or equal to 1. So anything that was smaller than 1, which is like this little section here, has to just disappear. Oops. I blew it. There we go. So the asymptote's out. This little negative section down here is out. So the graph starts at x equals 1 and goes over, and the orientation, as we said earlier, x gets bigger and bigger. The orientation is off to the right. Yeah.
Natural logs and logs are scary itself.
Yeah, they can be kind of tricky. Okay, so someone put in the chat that they wanted something where the sequence starts with a number which is not 0 or 1. Do you mean a sequence or a series? I'm guessing you meant a series or a sum.
Professor, that's a big question, and that was on the quiz 11. That one, the one I got wrong answer.
Do you remember what it was?
Yeah, let me open the quiz right now.
I'm guessing it was it's like a sequence is like you start with 1 to generate the sequence, but a series or a sum, you can have it start anywhere.
So the sequence of four n plus 2. And at the bottom the end equals 7, and it's gonna go to 10.
10. Okay.
Okay.
All right. So if it doesn't start at 1, then you can't use those summation formulas. So you have 2 options. You either have to figure out how to adjust it so that it does start at 1, which can be kind of tricky, or you can just start plugging in values and work your way from 7 all the way up to 10. And usually if you don't have to plug in a lot of numbers anyway, that's pretty much what I would just do, because a lot of times it's quicker. And for this one especially, then you don't have to adjust anything. So I would just start sticking in the 7, get a number, and then plug in 8, 9, and 10, and then you can just add everything up. So when n is equal to 7, what would you get?
30.
30. When n is 8,
34.
when n is 9,
38.
and when n is 10,
42.
42. So then you just got to add those up and get a total. So if you add the first 2, that's 64. What's 38 and 42?
80.
And then 64 and 80?
144.
144. So what I saw some people do is they use the formula for it, which would work if it was going from n equals 1 all the way up to 10. So if you got a number that was like a lot bigger than this, like I think if you go from 1 to 10, I want to say the answer was 240. I can't quite remember, but if that was what you got, that's probably what happened. So if it's not starting at 1, you can't use those formulas anymore. You just gotta kind of work it out.
Okay. How about it's not the distance from 7 to 10, but it's like bigger. I can't do the adjustment like that. Like
So like if it went from like 7 to 100.
Yeah, something like that.
Okay, that I wouldn't give you. I wouldn't give you a big one to calculate if you couldn't use the formula. I don't think that would be fair. Because I don't want you to plug in like 93 values to, have to add them up. But if it went from 1 to 100, sure, that one's fine. But I wouldn't do that to you.
For 11B on the study guide, would you solve it the same way of like just plugging in numbers? Because it has like it starts at 0 and goes to 6.
Yes. Yeah, so she's talking about this one, k equals 0 to 6 of sine of k pi over 2. So yeah, this one, the formula really isn't going to work either because it's not starting at 1. So I would just start plugging in the values and just see how they come out. So when k is 0, that makes the angle 0. So what's sine of 0?
0.
Okay. When k is equal to 1, now it's sine of pi over 2, which is,
Isn't it also 0? Or is it 1?
sine of pi over 2 is 1. When k is 2, now it's sine of pi, which is 0. When k is 3, you have sine of 3 pi over 2. And that's -1. K equals 4, be sine of 2 pi. Which brings you back to 0 again. When k is 5, sine of 5 pi over 2 is back to +1. So if you notice, you're just basically going around the unit circle, hitting those values on the x and y axes. So when you finally plug in like k equals 6, you have sine of 3 pi. So you go around the circle 1.5 times. So it just brings you back to 0. So if you total everything, it just gives you 1.
And I got a question. If it will only work, if you were to use the formulas, it will only work if the k is equal to 1.
Yes.
Okay, just making sure.
Yeah. So if it went from excuse me, 1 to 6, then those formulas would apply. But again, it's a trig function, so that can make it a little interesting. So with the trig functions, I would just do it out. But if it's a polynomial in there, like the 4n plus 2, if it went from 1 to 10, I would use a formula on that, because then otherwise you'd have to plug in, like, calculate 10 values and then add up 10 different numbers, which is fine if that's how you want to do it, but it might take you a while.
How would you solve a problem like 18E? It's like a limit.
Are you still on the study guide?
Yeah.
Okay. Let's see. 18E.
Yeah.
Okay. So the limit as x goes to infinity, 6x over root 9x squared plus 5x minus 2. So with the limits, as x goes off to infinity, you can use those guidelines that were discussed in the notes in the videos. So the guidelines say you pretty much just have to pay attention to the degrees of the top and then the degree of the denominator. So the degree of the numerator or the top would just be a 1. And then if you look down here in the denominator, it's not a polynomial, so it doesn't have a degree per se. But when you're looking for the degree, you only pay attention to the term with the highest power. So that 5x minus 2, you just ignore. Like it's not going to affect the degree at all. So the 9x squared, it's inside of a square root. So if you square rooted it, what would it become?
3x.
It'd be 3x. And now what's the degree of that term?
1.
It's 1. So when the degrees were equal like this, then your answer was the ratio of the leading coefficients.
6/3.
So 6/3. And then it's going to equal 2. So if you got a square root down there, or I mean, you might even have a square root on top, just take that, the term that gives you the degree and then square root it. And then you can compare your exponents. But square root it first, and then compare. So on F, it's the same, yeah, it's the same function. But it's X changed. So instead of going off to positive infinity, it went off to negative infinity. So it's not going to change a whole lot. Oops, -2. So you still do the same thing. You're going to take that 9x squared, root it to give you a 3x. And then you're going to also take the ratio of your leading coefficients, just like you did before. However, you're going off to negative infinity. So in the numerator, what's 6 times any negative number? Is it positive or is it negative?
Negative.
It's negative. Now down here in the denominator, these negative numbers all got plugged into here from the original. Well, but then you got to square root it after you plug them in. Well, if you square root anything except 0, what kind of a number did you always end up with?
A positive.
A positive. So the denominator is giving you positive numbers. So if you have a negative over a positive, what kind of a number is that?
Negative.
Negative. So it's a -2 as opposed to a +2. On 18E, since x was approaching positive infinity, the numerator was positive and so was the denominator. Like that didn't matter. But it definitely mattered over here because it changed the numerator to negative and the denominator stayed positive. So the square roots, you do have to pay attention to what x is approaching, if it's positive infinity versus negative, because that will affect whichever place doesn't have the radical, which in this case was the top. All right, how you guys doing on the sums or like these two infinite limits or limits at infinity?
I have another question about the limit, but on the module, for chapter 14.
Okay.
Yes. You see the question E on the page 7 on the module, chapter 14.
Okay. Let me pull it up. And say where it was again.
Page 7,
7.
question E.
Oh, okay. Oops. Okay, so this is the chapter 14 notes. Page 7. Example E, right?
Yes.
Okay, so that was the limit as x approaches 2. This is a good one. X squared plus 2x minus 8. All over x to the 4th minus 16. So with limits in general, your goal is to be able to plug in that number. So just try it and see if you can. And you'll know if you can't because if you plug it in and it comes out with a 0 in the denominator or a 0 or a negative inside of a radical or something like that, then you can't plug in that number. If it gives you an answer, then great, it gives you the answer and you're done. So if you plug in the 2, does anything bad happen?
It's going to be 0.
It's going to be 0. So we can't plug it in, which means we have to manipulate the function. And since it's pretty much just polynomials on top and bottom, your only option is to start to factor and hopefully get things to cancel out. That will then allow you to plug stuff in. So the numerator, what would that factor into?
X plus 4 times x minus 2.
Yeah. And then your denominator, x to the 4th minus 16, that's just a difference of squares. So that would be x squared plus 4 and x squared minus 4. So nothing cancels out. So you still can't plug in the 2 because it's going to end up giving you a 0 in the denominator. And right there, that's where it would happen. This term, it wouldn't, but this one it does. So you're still stuck with it. So you got to keep factoring until you can plug in that 2. So the top is done. You can't do anything with that. The denominator, x squared minus 4, that's another difference of squares. And now you have an x minus 2 on top and bottom that you can cancel out. So those are out. And so now if you plug in the x equals 2, you can actually get an answer. So if you plug it into the top, that would just give you 6. If you plugged it into the denominator, what's 2 squared?
What should it be?
What's 2 squared?
4.
4 plus 4?
8.
Okay. And then if you plugged it into the second set of parentheses, that would just give you a 4. So you can reduce them. You can take a 2 out of the 6. And then you can take another 2 out of either the 8 or the 4, but not both of them. Just take it out of the 4.
3 over 16.
3 over 16.
not clear for me.
Oh, that's not what I got as an answer. I got 1/8. Oh, I think I know. Yeah, there is a mistake in there. And then the key, if that's what you're looking at, that should have been a 2 + 2 down in that denominator. Is that what your question is? If you're looking at the key for the notes, there was an error in there.
Yeah, that was my question. Yeah.
Okay, yeah, the 2 got transposed into a 4 in accident. Okay, so it should be a 3/16.
Thanks, Professor.
You're welcome. All right. What else do you guys have?
How about on the last quiz, question 6, the expansion, what is the coefficient of the fourth term when expanding to x + 3 to the fifth?
It's 3 to the 5th.
Yes.
Okay. So
The
we have
coefficient of the fourth term
fourth term.
when expanding.
All right. So you have two options with this. One option, which would definitely not be the preferred, but that's just to start multiplying this thing out, which is foiling upon foiling upon foiling upon foiling. So it's definitely possible, but it's going to take you like 20 minutes just to get that all worked out. So the other option, which is going to be a lot faster, is that Pascal's triangle. You just got to make sure you're choosing the right row and that you have the right numbers to get stuck in there. So Pascal's triangle, I'll do it up here. That's where the top number was 1. Second row was 1, 1, and then it started to do a pattern all the way down.
Yeah.
So are you wondering how the pattern works?
Well, no, you know what? I used one of the formulas, and that's where I thought maybe I went wrong. Should I just stuck with the Pascals? Was that the idea?
I would. You could. Are you talking about like the binomial expansion?
Yeah, it was in the book.
Yeah.
Okay, yeah, you can use that as well.
That one was
Some
much
people
more.
are really good at it, and some people are really not. So they didn't really
Backfired on me this
well,
last quiz.
it's like you either really get it or you just really don't. It didn't. It's not. Well, I sort of do. It's like, but so yeah, so you can totally use it. It's fine. Pascal's triangle, more people seem to get that and are able to reproduce it in the binomial formula. And they can remember how to make it a lot quicker than they can remembering how to do the binomial stuff. But either way is good. So if you use the binomial formula, that's totally fine. Because it's not going to tell you how to do it. It's just going to ask you like, well, what's the fourth term or what's the eighth term or whatever. All right, so it is x + 3 to the 5th, right?
Yes.
Okay.
Yes.
All right, so that means we're going to be choosing this row. That's 1, 5, 10, 10, 5, 1. Okay, so just take your first variable in there, the x, or sorry, the first term, and you're going to raise it to the fifth power, since that's the exponent on the outside. So it's x to the fifth. And then the powers just decrease all the way down. So to the fourth, the third, the second, and the first, and then after the first, you run out. Because it'd be like x to the 0, which is just 1. So then take the second term, the 3, and raise it to the fifth power, but now you're going to work your way from right to left, so just go backwards. So the fifth, the fourth, the third, the second, and the first, and then you run out again. So we're only interested in the fourth term. So 1, 2, 3, 4. So this one. So I mean, you can work out all the other ones if you want to, but if you only want the fourth term, let's just stick with that. So 3 to the third, that would just be 27.
27,
27 times 10.
270.
So your coefficient of the fourth term is just 270.
Yeah,
Way easier.
that seems a lot easier than the route I went. But I think in the homework, it had us using the formula. It turned out to be
Which you can do, but you can, I would just use Pascal's triangle. Unless, I mean, if you really like the formula, then totally use it. Like, I'm not going to be specific which way to go. Just use which one you like the best.
yeah, Pascal seems like an easier route.
Personally, I like it a lot better because I can reproduce it, and it's more, I don't know, kind of rote, as opposed to having to recall the binomial formula, and it's less involved. So I don't know, but if you like the formula, go for it.
Well, it worked on my homework, but it didn't work on my quiz.
Oh, dang it. Yeah, that's always a fun little dilemma. Just as a side note, I was looking back at this example that we did up here, mainly when we had the 6, the 8, and the 4. Let me show you something, because this is particularly useful when you've got sums. You've applied the formula. And you end up with like a lot of numbers to multiply, and things can start to kind of go crazy real fast. So I don't know, let's just say it comes out to this. For whatever reason, it comes out to this. So you have 8 times 6 times 7 times 2, all divided by 6. And what I see the majority of students do is they multiply 6 times 7 times 2, and they get that total, and then they divide by 6, and then they multiply the result by an 8. And that's totally fine. It's not wrong, but it's probably not the best way to do it. So when you've got a lot of numbers to multiply and divide, what I would do is start to divide first, because if you divide, that makes your numbers smaller right away, and smaller numbers are always faster to multiply out than big ones. So if you look at this expression, you can start to simplify in mainly the 6s. They would just boom, boom, cancel out. And now your multiplication just got a lot faster and a lot easier to do. And multiplication, it doesn't matter which order you go. So you can multiply the 8 and the 7 together, then the 2. You can do the 7 and the 2, and then the 8. You can do the 8 and the 2, and then the 7. So it doesn't matter. Just go with whatever you think is the easiest. For me, I would do the 8 and the 7 first, because then you just have to double it. So like 8 times 7 is 56. And then if you doubled that, that would equal
112,
something
something like that.
Yeah, 112. So for your sums, if you're getting stuff like this, I would always try to reduce things out before you just started to just multiply stuff together. Because if you multiply that out, you're going to get a really big number, and then now you're going to just have to divide big numbers. So let's say it was 1/30 times 60 times 27, times 5 all over 6. So kind of the same concept, but not nearly as direct as this one. So here you've got a lot of options, or you've got a couple of options that you can kind of go with. And it doesn't matter, where you divide things, you can just start to divide stuff. So some people would go the 30 into the 60. Some people would go the 6 into the 60. Some people do the 6 and the 27. Some would do the 30 and the 27. It's not going to matter as long as it reduces, it reduces. I would do the 30 and the 60. Then you get the nasty looking numbers to just kind of go away, the big ones. Well, now you can do it again with the 2 and the 6. So the 2's out of there. The 6 becomes a 3. And you see anything else you could do?
The 3 and the 27.
The 3 and the 27. So now you've taken this really long multiplication problem and you've turned it into just 9 times 5. Which is a lot faster than having to go 60 times 27 times 5 and then trying to divide that by 180, which you're more than welcome to do, but speed helps sometimes. So take these multiplication division stuff and see if there's stuff you can reduce. And if there is, then great, you can move on. If there isn't, then yes, you are stuck with having to multiply stuff out. But anyway, just thought I'd go over that, just, hint, hint. Okay, so we've done parametric equations quite a bit. We've done a little bit with the sums, Pascal's triangle, a little bit on limits.
I have a question on 20A. It's on continuity.
Continuity, okay. Or from the study guide?
Yes.
Okay, so 20A was discuss the continuity of the function if there is a discontinuity, then classify it as either removable or non-removable. So the function for that one, it was cosine, wasn't it?
Yeah, it was
Cosine of pi x over 3. Okay, are there any numbers that you're not allowed to plug in for x? Like, do you get a 0 in the denominator for anything? Do you get a negative inside of a radical? Do you get a vertical asymptote out of there?
I don't think so.
Okay, so if you can plug in anything you want, like there's no restriction on X, then it's continuous on the entire real line.
Is there any trig functions that would have like a restriction?
Sure, which ones have restrictions?
I think the tangent one, and I don't think the sine one does.
Yeah, tangent does. I mean, can you think of a trig graph that has a vertical asymptote? Tangent's one of them. What are the others?
Cotangent?
Yep. There's two more.
Oh, I forgot what it's called. It's cosine, the little -1 thing.
No,
Inverse cosine.
not inverse cosine.
Wait,
That's a different function.
I know what it looks like.
Can anybody else help her out? So the ones that have vertical asymptotes are tangent and cotangent, and which other two functions?
Oh,
Oh,
I know what it looks like.
It's like, yes, but if you don't know what the function is, it doesn't really help you. One of them starts with an S, and the other starts with a C.
secant and cosecant.
Secant and cosecant.
Yeah, those.
So yeah, so
You know what
those,
you're talking about.
it was coming. If there's a vertical asymptote, that would be where you would have a discontinuity. So like tangent, cotangent, secant, cosecant, they have infinitely many discontinuities because there are infinitely many vertical asymptotes. Whereas opposed like 7b, if you, or 7b, 20b, that one, we can factor the denominator. So x squared minus 2x minus 48, that's just x plus 6 and x minus 8. So before you reduce it, what makes the denominator 0?
8 and -6.
8 and -6. So those are your two discontinuities. So it's continuous everywhere else. So you got to skip over the -6 and then skip over the 8. So that's where it's continuous. And then you have a discontinuity at the -6 and the -8. But you got to classify them. So they're either going to be removable or non-removable. So if you have no idea what it is, you have a 50-50 chance of getting that part right. But if you go back to your original function, it reduces. So what actually cancels out?
The 6 part.
The x plus 6, yeah, that's gone. So which one of these two numbers came from the x plus 6? Which one of these two numbers made x plus 6 equal to 0? The -6 or the 8?
The -6.
The -6. So isn't that the term that you just canceled out or removed? Yeah. So that is the removable discontinuity. The 8, it's still in there. That's the 8 still makes the function not work. It still makes it not continuous there. So that's the one you did not remove, or the non-removable. So whichever factor cancels out, its 0 is the removable discontinuity. And whichever factor didn't cancel out, its 0 is the non-removable. Okay. Someone's asking a question or posed a question in the chat. Ugh. It was on a sun. And this one's kind of come up in different places with different problems, but they're all kind of the same type. So I'm just going to make one up. So let's say you have the sum from 1 to infinity, 9 times 3 to the n minus 1. Would this series converge or diverge?
Diverges.
It diverges. And why does it diverge?
Is it the 9 plus 3 is greater than 1?
It's just the 3.
Just the 3.
Yeah. So the 9, that would be your A value, and the 3, the thing with the exponent on it, that's the R. So yeah, so he's right. The R is bigger than 1, but it's going to diverge. Oops. What if it was this way? 9 times 1/3 to the n minus 1. Does that diverge or does it converge?
Converge.
Mm-hmm. Since now the R is 1/3, and it's less than. So most people are really good with that. They're fine and dandy. However, throw in a little curveball.
Yes, you did.
It messes with you. So 9 times 3 to the 1 minus n, and I would say at least 1/3 would just look at that and go, oh, that diverges. However, you can't determine that yet, because what's off about it?
The n minus 1 has to be 1, or the 1 minus n has to be 9 minus 1.
Yeah, your exponent's different. In order to see if it converges or diverges, it has to fulfill that format. It has to be, the sum from 1 to infinity of a times r to the n minus 1. That is not what you have. You have 1 minus n. So you got to play around with it before you can just decide if it's going to converge or diverge. So if you want your exponent to flip in sign, so in other words, you want all the signs to flip, all the positives to negative, all the negatives to positive. That means you need to take the reciprocal. Because if you take the reciprocal of a number, that makes your exponent negative, right? Because what's 1/3 to the negative 1? Oops. 1/3 to the negative 1 is 3. And then when you have an exponent to an exponent, what do you do with them?
Add them.
Not add,
You mean on when you're multiplying?
you multiply. And so that's how you're going to get all of your signs to flip, because you have a -1 times a 1, and then a -1 times a negative n. So the n is now positive, the 1 is now negative. And now you know it converges. So if your exponent is backwards from what you want it to be, you got to take the reciprocal, and then that'll flip your exponent to that proper format. Okay, now just for practice, let's figure out what it converges to. So do you remember the formula? Like if it's a convergent geometric series, an infinite series, it has a nice little formula that you can use to figure out the sum. And since we're running short on time, we'll just give it to you. It's a over 1 minus r. So with this sum right here, what's the a?
9,
9. And the r?
1/3.
1/3. Okay, so now you just got to start working stuff out. So like, what's 1 minus 1/3?
2/3.
2/3. And when you divide by a fraction, it's the same thing as multiplying by its reciprocal. So instead of dividing by 2/3, let's multiply by 3/2. And nothing cancels out. So you're just stuck with 27/2. So yeah, you got to be careful of the exponents backwards. So for the sums, for any formula to apply, it has to be in that proper format. So your exponents have to line up. Your start number has to line up. If anything is off, then you can't use the formula. So you either have to manipulate it to get it there, or to start plugging in numbers. But this one, don't start plugging in numbers. If it's an infinite series, don't do that. But if it's finite, then you could. Okay, so we got probably time for like one more thing or concept you'd like to go over. Look at the You guys okay with like on the study guide, it was number 19? Yeah. That's the one where you had to evaluate the limit using the graph.
Oh, I love that one.
Oh. These questions, it's like it's a love-hate relationship. You either like them or you just hate them.
I also think the graphs just look funny because it's like, what is that?
Yeah. For these problems, like, don't get stuck on like, well, what function is it? Like, you don't care. You just want to know what the limit value is. So the graph might look crazy. You might not have ever seen it before, but that's okay. Don't try to figure out what the function is. Just get the limit. Because the function is not really going to help you. And most of the time for a problem like number 19, the function would be a piecewise function. So it would take you a while to figure out the exact function of that thing. And then once you got it, it'd be like, well, now what do I do with it? It doesn't help me.
I sure just want to make sure on the question 19, I remember you said when the solid dot
Uh-huh.
met the blank dot, so we got so the solid dot win, right? Like
Yes. Yeah, as far as like the function value.
yes.
Yeah. So like, so if it was asking, I don't think it asked this. So on number 19, if it wanted to know f of 2,
Mm.
it didn't ask you for this, but just in case, if it wanted to know f of 2, then yeah, now you're looking for the actual point, not the open circles or the holes. So for f of 2, that would equal 3, because that would be where the point is. And then it didn't ask this either, but just in case it does, what is f of negative 2?
The 6.
It'd be 6, because again, that's where the point is. So yeah, you're looking for the point or the closed circle to give you the corresponding y value.
All right, got it. Thank you.
You're welcome. All right, well, I think that is going to be all the time we have for today. But please email me or contact me with your questions if you have any. And I will get back to you with an answer that will hopefully make sense.
Thank you very much.
You're welcome. So yeah, just don't forget the quiz is due Friday as well as the exam. You can use the quiz, like if you take it early enough, the quiz will show you like maybe gaps in your knowledge that can help tell you what to study for the exam. But go back, look at the old quizzes, look at the study guide, the notes, the homework, whatever. Email me questions. One more thing too, if you're asked for an access code in Proctorio, I do not have an access code to give you. That is Proctorio's fancy way of saying, hey, there's a problem. So it can usually be fixed by updating either Chrome or Proctorio or both. But if it's anything beyond that, like that doesn't fix it, you'll have to contact Proctorio because I am not a programmer with Proctorio. I don't know how their software works or the ins and outs of it.
Sometimes it pops up if you like do it. I think it's in modules versus like, or like if you use the syllabus one over the modules one, it pops up. I don't know. I know.
Say that again?
Like,
What'd you just say?
so like it also like depends on like where you like click on like take the quiz, because if you click on it in the syllabus, I think it like pops up with a like you need an access code, but if you click module or somewhere else, it like doesn't do that.
Where's the somewhere else?
He's like, I know one of them does it.
That's weird. Okay, that I did not know. Do you have a quizzes? Does it work if you click on quizzes?
I think that might be where it was working.
That one? Okay, that's weird that it would work one way but not the other.
But I was like, I'll just keep playing around with it until it stops saying that.
Yeah. I know from myself, to get Proctorio to even like show up this week, like over the weekend, I had to update Chrome first, and then it was fine. So I know recently Chrome's had an update. So there you go. But yes, I do not have an access code to give you. So if you ask me for one, that's all I'm going to tell you. Is like there isn't one to give. Why it just doesn't tell you to update, I don't know.
Yeah.
Okay, take care.
You're welcome. All right, we'll talk to you guys later.